Well, I think we can officially get started. Welcome back, everyone. We're almost at the weekend, closing out week 6. And probably the biggest thing I want to talk about is we're also going to restart our second cycle for exam 2 now. What I'll be doing on Friday is getting everything in line on this part of the Canvas page down here. I'll say what the coverage is for the exam, include the same kind of documents before for review problems on that exam. And so if you'd like to get started early reviewing for exam 2, you'll have that opportunity. Probably sometime Friday afternoon, this information will get posted. I'll try to work on this a little bit quicker, probably even before grading the papers. Then after that's done, I'll get the papers graded, sent back to you as soon as possible. Hopefully not on Sunday. I'm trying to avoid grading on Sunday, but sometimes it's the catch-up day, it turns out. So that's what we'll be doing. When we come back on Tuesday next week, I'll be sending you information probably to early Tuesday morning or maybe early Monday morning on scheduling your exam. If you're in the in-person section, then you'll just come to class normally, like you did for exam 1. And again, it's pretty much just a complete redo of everything we did from week 1 to week 4 on our first exam. Any questions, folks, with the upcoming exam or otherwise? Okay, well, for today's class, we're finally turning it over to chapter 2. We're not going too far into chapter 2, but it's in fact a pretty big chapter. It's a cool one to read in its entirety if you had all that free time. It gets a little bit more into the applications of things like computer graphics and such. It's a more concrete version of chapter 4. But our objectives for the math department on this course is to work a little bit more abstractly. So that's why we'll take just 3 seconds out of chapter 2. In chapter 3, we'll talk a little bit about a new operation, determinants, and then we'll spend a lot of time in chapter 4 covering that one really carefully. So what section 2.1 is all about is it says matrix operations, but specifically we'll be adding, subtracting, scaling, multiplying by a scalar, and multiplying matrices. Other random operations like transposes. There's no division by matrices here. We can't literally divide by a matrix. Instead, we'll do the next best thing of seeing how to invert matrices. So that's our goal for today. It all starts with a lot of sections that you might notice in this in linear algebra, just a humongous wall of text. But really, we're just going to settle down what we mean by certain common notations. There's a reminder that pretty much what we're doing in 2.1 for the first half of the notes is literally just kind of a do-over of what we did in section 1.3. The landscape is just bigger. We're dealing with matrices as opposed to vectors like when we were in this section over here. So first, the big bit of notation is if we have an m by n matrix, like we've recalled before, that denotes m rows and n columns in our matrix. And the next new thing with our notation is the ij entry of the matrix A. When we write down something like aij, call it the ij entry of A, we just mean it's the entry in the ith row and jth column. So we can now indicate a matrix by the variable expression, usually uppercase letters at the start of the alphabet. We can say what the entries look like by just writing bracket aij. We'd have to specify how big that matrix is. So this one looks like it has m rows going by where the red dot is, by n columns. And if we want to be really, really specific, we might write out the matrix in this particular format. We'll do that a couple times even in these notes, just to show how certain operations will really go component by component. It's definitely clunky. The dots going this way means this is entry 1 on row 1, entry 2 on row 1, so that's the second column, that's why there's a 2 there, and so on, entry 1 on column n. Then same pattern on row 2, dot, dot, dots means there's loads of columns here, n could be a very large number, and then same repeat here, and then diagonal dot, dot, dots as well. So that's our standard notation for indicating the matrix. Other things we've done just for a way to review all of our notation is we've often done this. In fact, we've done it quite a lot. If we want to just emphasize the columns, we might call this column one, maybe V1, maybe U1, or simply just A1. Column two could be listed as A2, column three here, or excuse me, column N could be listed as AN. And that's all we would be expressing here if we indicated the matrix A. We're just saying, what are the variables for each column vector? So that's a lot of terminology, but we've been plugging away at it quite a bit throughout the notes. The major new thing is the AIJ notation. Any questions at the moment with any of the notations so far? Okay, for just something more concrete, let's suppose we have a matrix A that goes, let's go for something that's maybe 3 pi 2, nothing too large. Maybe we'll have a 7, 8, -3, just random numbers here. 0, 5, 17. Seem to pick a lot of prime numbers when I do this. So here's our random matrix A. If we were to indicate the entry for maybe the A32 position, A32 would just tell us to go down to the third row. That's what the first three is indicating. 2 means go to the second column. So that would be 17 itself. Notice if I had actually maybe 13 rows, you might actually have to comma separate these because it wouldn't be clear what the digits are corresponding to, columns versus rows. So if you want to be hyper specific, you could put a comma right there, but if it's contained, there's less than 10 rows, less than 10 columns, the first digit is the row number, the second digit is the column number. Occasionally, you might have to use commas for bigger systems. Just for another random one, if we said A12, that would mean go to row 1, column 2, and that would be the number 0. So that's just a way to index into the matrix itself, corresponding to its entries. Other things we can talk about are the diagonal entries. This takes a special role, particularly if the matrix is square. But we could talk about the diagonal entries of any matrix whatsoever, even if it's non-square like this one. Diagonal entries are kind of nice to indicate. They repeat the column and row number. So they would be for AIJ, A11, A22, A33, if that exists, and so on. So in this particular matrix, the diagonal entries are here. This is A11, this is A22, and these are the diagonal entries. We sometimes call this entire strip highlighted in yellow the main diagonal of that matrix. And so far, that's pretty much our major terminology. These matrices are going to have a really special role down the line. A diagonal matrix means it's square, and the non-diagonal entries are all 0. So just a couple examples of diagonal matrices would be things like these. Diagonal matrices. It wouldn't be this because this is a non-square matrix. When we say a diagonal matrix, the n by n is telling us only specifically square ones. So one diagonal matrix could go like this. The non-diagonal entries are all 0, and those would be entries here and here. This would be the main diagonal, and they could take on any number whatsoever. They can in fact be 0, 0. That would just mean it's the 0 matrix at that point. Or it could be something like 1, 3, and that would make it diagonal. Another example of a diagonal matrix we've looked into is, say, I3 or I2 or any identity matrix. Identity matrices just have the specific requirement that the main diagonal itself, it consists entirely of ones. So that's the only thing new with an identity. But it too is a diagonal matrix. The I3 diagonal matrix would look like that. So that's pretty much our main examples of new interesting matrices we'll look into. Again, some of these have really special roles, like the diagonal matrices in chapter 5. Identity matrices have already come up as important. And they're a big deal in this section because multiplying by an identity is like multiplying by the number one when we get into matrix times a matrix multiplication. Last interesting one is the zero matrix. Any zero matrix can have non-square size. So if we had maybe the 2x3 zero matrix, I would hesitate to put a vector in front of it because that might imply we're thinking of a column vector. So I would just write it as 0, and it would have to be clear from a context. This is not a scalar 0. This is not a 0 as a vector. This is 0 as a matrix that has this size. If it's 2x3, it would look like this. 2 rows, 3 columns, all consisting of 0 is the 0 matrix. Oh, Control Z got a little crazy there. Is the 0 matrix in R2x3. We say R2x3 because the size of this matrix is 2 rows, 3 columns. And this space contains all matrices of that same size, whatever entries you'd like to put in. Well, that's our review of all the notation. We need kind of a breather, so here's a quick example to take a look at down below. And so far, this is mirroring the section 1.3 notes almost pretty much verbatim. The moment you define matrices, and we've done it for a while, you might also want to talk about matrix equality. And it's kind of wild that this is the first time matrix equality has come up. We've been using the squiggle line for row equivalence. That wasn't matrix equality whatsoever. Those are just row operations to assist us in solving systems of equations. So this is actually the very first spot we've talked about what does it even mean for a matrix to be equal. We've informally said what it means, but here's the definition. 2 matrices are equal if they have the same size, so that's very important, and if their corresponding columns are equal. Or said another way, you have 2 matrices equal if and only if every single corresponding entry is identical. So here's a section of 4 matrices you could say, although one is usually called a column vector, the other is typically called a row vector. For which ones are equal? Well, A and D have the same size, 1, 3, 2, negative 4. They have the same columns, so we can say A is equal to D. And the next part's kind of debatable depending on your point of view. What would you all say for these two? Would you say they're equal or not equal? It does have the same entries, right? And they both have 3 entries. So what would make them not equal? It's that part right there. They have to have the same size, and we are being extremely specific when we say that. We mean this in the most literal sense. So when we look into the size of this one, it has 3 rows and 1 column, so this is 3 by 1. When we look into the size of this one, it's 1 row and 3 columns, so it's 1 by 3. That would tell us they have different sizes, and so they're not equal. B is not equal to C, despite them both having 3 entries. Despite those corresponding entries going down or going left or right being identical, they're not equal because they do not have the same size. And that does definitely seem weird in a certain sense. It'll make more sense when we start multiplying these matrices. You can take B times C, and you can also take C times B, and the results are wildly different. One of them is going to be a scalar, one of them is going to be a 3 by 3 matrix. And so it's in that sense that this is a sensible thing to do. Algebraically, they're different objects. Well, any questions, folks, about matrix equality at the moment? Okay, going on down the line. After you talk about matrix equality, we want to also think of this as being a vector space. In fact, this vector space is really not too different than these vector spaces like R3. There's in fact, an isomorphism in the background that tells you any algebra that you do with relation to vector addition and scalar multiplication is essentially the same in R3 versus R2 by 3. The only thing that's essentially different is the dimension. This would have dimension 6 because there's 6 components, whereas these would have dimension 3 because there's 3 components. Vector addition in the land of vectors was just add up the components, going component-wise. Scalar multiplication was scale all components by the common scalar c. And then we got some nice algebraic properties. Those two operations turned R3 into a vector space, and the same analogous thoughts look like this. I wrote here, this should feel like deja vu, and that's because if we indicate a matrix, A is Aij, that's what the entries would look like. B is Bij. They both have the same size. That's what this implies when they say they are in R m by n. Both matrices have m rows and n columns. Then vector addition looks like this. If A is indicated this way, then entries go A11, A12, A1n across row 1. Likewise for matrix B. So adding A and B together, all this stuff is just saying is add the components in the corresponding order. So add the 1, 1 components together, add the 2, 1, 2, 1 components together, and so on. Again, should feel like you're doing the same exact thing when you were down here doing that vector addition. That's kind of comforting in a way that we have the same kind of algebra so far. Scalar multiplication goes exactly the same as well. We scale every single entry by the common scalar c when we do c times a like this. So putting those two operations together, Rm by n is now a vector space, just like R3 was. We have some of the common algebraic properties that we often take for granted. Commutativity of the vector addition holds, so does associativity. Adding the zero vector returns the original matrix A, so we have an additive identity. We have a type of distribution with the scalar, and we can also distribute A through as a matrix, and another type of association with scalars as well. So these are things that we essentially just take for granted whenever we're working out computations. And what we'll do is, again, very similar problem to what we did when we were way back in section 1.3. Just practice with these vector space operations. So I have 3 random matrices put down. We'll do as many of these computations as we can and mention when they're undefined. But any questions first about any of these operations? Okay, let's give this a try down below. So first is 2a minus b. A and B have the same size. They're both 2 by 3. So this is an operation that we can do. 2a minus b then becomes. First thing I would do is just rescale A. We're scaling A by the scalar 2. That just means double all the entries. So we'll go 2, negative 4, 0, 2, negative 8, 0. Then plus, I'm going to rescale this as well. Minus b just means add negative 1 times b. So I'm going to multiply all these by negative 1. That's a personal choice. You could go minus and then just copy b. I think I mentioned a couple times, this is just easier for me to not get mixed up on negative signs. Now we're doing what is still called vector addition. Again, that's weird, right? Because these are matrices in their own right. The reason we still call it vector addition is it's now a vector space. And vectors can be all sorts of things. They can be vectors in this sense. They can be full-on matrices, or they could be functions like e to the x, cosine, and so on. If you have the right algebraic properties, we still call it a vector space, even though these are bona fide matrices we're adding now. But this is just done component-wise. So I'm in the 1, 1 component, 2 minus 4. It's going to give us negative 2. I'll go row-wise, 0 minus 3 for a negative 3, negative 8 plus 9 for a positive 1, then negative 4 minus 1 for negative 5, negative 5 again, and 0. Let me know if you notice I mess up any of the arithmetic there. There's a temptation to go fast because it's simple arithmetic, but then that's what does you in on your accuracy. Well, this was essentially just a redo of this problem when we did 3u minus 2v. Algebraically, it's the same exact process. That's kind of cool in a way. But they just look different now written as matrices. So next up is b plus c. Taking a look at this is the first time we run into a problem, right? The matrix B is of size 2 by 3. The matrix C is of size 2 by 2. And when it comes up to the addition here, we just can't do anything with that. We could sure add up the first two columns together, but then we're stuck. There's nothing to go along with negative 9, 0. So in this case, we would say the operation is undefined since BC have different sizes. And that's 2 down. Next is C minus 6 times I2. Here we just have to know whenever I or I2 comes up that this would be the identity matrix. It could have been written this way, but I feel like that's even more tricky in a way. If you see C minus 6 times I is still the identity matrix, and now we have to use the context to tell us that should be the 2 by 2 identity matrix. I think that's kind of not nice to do, especially on an exam setting. That could be something you see in the homework more often. On the exam, I'll be more specific because I don't want a question where you might say, well, this is undefined if I is of size 3 by 3, for example. This is now definitely defined. Both C and I2 have the same sizes. So I'll do this on the next page. C minus 6 times I2. First thing I would do is just write down C. It goes 4, negative 1, 12, 6. I'm going to add the next matrix. Scale I2 by negative 6. We never wrote down I2, but just for a visual, I2 is 1, 0, 0, 1. So scaling it by negative 6 is just going to the main diagonal and replacing 1s by negative 6s. Which makes this kind of a special operation in a way. Whenever you're adding or subtracting a constant multiple of an identity matrix, all you're doing is operating on the main diagonal. Everything else is the same. And we can see it due to those zeros there. So we're going to get, going column-wise again, 4 minus 6 for a negative 2, and then a 0. So it's 1 minus 0 for negative 1 minus 0 for a negative 1. 12 plus 0, so just 12. Then 6 minus 6 for a 0. And that's where it ends. We did a couple linear combinations of the different matrices. One was undefined. And again, kind of just a relaxing, basic arithmetic kind of problem. Really, the whole point to example 2 is just getting used to these features in this new looking vector space. Any questions at all, folks, on example 2? Okay, we have other interesting operations going on beyond vector addition, scalar multiplication type operations from the vector space structure. We also have matrix multiplications. This is where the note starts to get pretty interesting, I would say. And I have a lot to say about matrix multiplication in a very, very short amount of time. We'll talk about some cool facts about it as it relates to linear transformation. If you want to see some of the cutting edge uses of this is a video from just 2024, so it's already kind of old information on how matrix multiplication is being used for AI and other interesting things. In fact, recently, AI has found a way in high performance computing to speed up the process of matrix multiplication. And think of that as a really interesting thing because we use matrix multiplication to train AI, and AI itself has found a better way to train itself, optimizing matrix multiplication. So that's the cool things that are going on now in 2025. It's a long video, but if you have the time, maybe break up doing your homework or reading the book. This is a good one to just take a cognitive break, do something slightly different. And here's our first look into what matrix multiplication really looks like. My goal is to try to convince you it's not too different from what you've done before. So let's call this a warm-up. If we take A times a vector B, we're doing stuff that we did in chapter 1. I believe that was section 1.4. I'll put down just a random matrix A. Let's put 1, 5, negative 1, negative 1. Random scalar B, let's go 7, 2. So here's our refresher. What we do is we take the row and the column, take the corresponding entries, multiply them, and add them up. So this will be 1 times 7 for positive 7, plus negative 1 times 2, so 7 minus 2, for value 5. Then to get the entry 2, we just move down to row 2, and same process. 5 by 7 for 35, minus 2 gets us down to 32. And that's what a matrix times a column vector would look like. Now we can scale this up and actually put a matrix here. Above, this tells us how this will go. If A is an m by n matrix, and B is an n by p matrix, those values n are important. If they are different, the whole thing is undefined. But that's just like how if this is 3 by 2, and this is 2 by 3, inner dimensions had to match there, or else the matrix multiplication and the vector was undefined as well. So if we have the right size matrices, look at the inner dimensions, this will tell you if the product is defined. B1 through BP are just the columns of the matrix B. And the product of A times B is an M by P matrix. That's just going to be this dimension and this dimension coming from the number of rows and the number of columns. And that's the same thing that goes on here. This is oh, hang on. Let me get my number of rows correct on there to start off. I didn't notice that till now. This is 2 by 1. Not sure where those threes came from. Sorry for that distraction there. The result is a 2 by 1 column vector. So the outer dimensions here and here, same as back in section 1.4, match up to the size of your product. Sorry for the weird 3 by 2, 2 by 3. I'm not sure if I was taking a little nap or something like that, a micro sleep. But the way we define A times B is we just do a bunch of matrix times column vectors. So it would look like this. A times, here's B written out as columns. The very first entry or column is going to be A times the first column of B. The second column of the product is A times the second column of B, and so on. And that's essentially what these look like. It's just a bunch of multiplications going in that way. So if we take this skill that we learned right here from 1.4 and just up the size, we're essentially not doing anything different. So we'll practice that down below here. First, any questions before we get started? Okay, so I've got two random looking matrices. They're of different sizes, but that's okay. We're not adding or subtracting them. We can definitely multiply them, potentially. First, we'll look into A times B. And this is one of those things where you definitely want to look before you leap. A is of size 3 by 2. B is of size 3 by 3. And on the very first one we're looking into, this is undefined. There's a lot of ways you could say this if you're ever asked to give an explanation. If you just point an arrow at this, that works for me. That's the whole punchline. You could say the number of columns in the matrix A is not equal to the number of rows in the matrix B, and that's the exact reason it's undefined. If you want to paraphrase that, you might say the inner dimensions do not match. So that's kind of a weird problem to start off with, but it's good to know when things can't be done before you go to try to crank them out. So maybe this is the first most important example before we even get started. So A times B is undefined. Next, we'll look into B times A. So if we go B times A, this time B is of size 3 by 3. Matrix A is of size 3 by 2. There's a match here, so this is a defined product. We can proceed to the next step. And the next thing I would personally always do each and every time, and I know it's tedious, is copy down those matrices. 0, 4, 8. Some people don't have to do this. Some people have really, really good visual skills, visual memory. But for me, if I'm trying to do this as accurate as possible, I need to have my eyeballs right here with both of the matrices put together. So here's the matrix A substituted in. Let me double check I have all the entries in. Okay, I think we're ready to start. We can automatically say that this is going to be a 3 by 2 result. That 3 and 2 came from the outer dimensions. This 3 and that 2. So now we have a size expectation of what we should get. And now finally, what I'm going to do for my matrix multiplication is just build out the columns, because that's what we're good at. That's what we've been doing in section 1.4, and it's came up several times. So my method is going to be all about focus on this column. Pretend nothing else exists. Some people literally put their finger on that one and just walk it down. Next, we're focusing on just that row and nothing else. And that gives us this entry here. It's kind of like when we multiplied across that way and got the entry 5. Same exact idea. So we'll take 0 times 2 for a 0, -1 by -3 for a +3, plus 0 again. So this comes out as 3, and we're done on that one. Keep your finger or your eye targeted to this one. The only thing that's going to change, just like in the warm-up example, is we go down a row, we use the same column to get the next entry, this one down here. So I'm changing the rows on the matrix in front, the one that's pre-multiplying, and I'm fixing the column on the one that's post-multiplying, this one out here. So same correspondence, 4 by 2 for an 8, plus 0, plus 2 is going to give us a 10 altogether. Then move down a row, we're on this one next to get that last entry. It's 8 by 2 for a 16, plus 3, so we're up to 19, plus 7 for a 26. And that builds out column 1. Again, it's just doing the same kind of idea up here. And we're halfway done. Any questions at all, folks, getting column 1 built? Okay, next, once we finish out the last row, getting the last entry down here, let me get rid of all this highlighting so it's not a distraction. We just move our focus onto the second column and do the same exact operation. Now we're building out what goes here. We start with row 1, multiply as if we're doing this again. Only difference is we're putting it into the second column. So this will be a 0, -1 times 4, so a -4, plus 0. So -4 to start. Then move down a row, keep the column. We'll have 4, plus 0, plus 12, so we're up to 16. Then once again, this becomes redundant to say, but this is the major skill. Move down a row, keep that column fixed, and do it all over again. This is going to be 8 minus 4, so we're at a total of 4, plus 42, so we're at a total of 46. At that stage, we did it, folks. That's the whole skill of matrix multiplication. It directly builds off what we were doing over here. In fact, that's what the definition is saying. This is A times the first column, 2, -3, 1. And the last one is just the matrix A times the second column, 1, 4, 6. So matrix multiplication is kind of cool in a way. It's a lot of arithmetic, and this is a skill you definitely want to practice quite a bit of. So there's plenty of that in the homework. Any questions at all doing this product here? Okay. Matrix multiplication, again, has lots of interesting applications, lots of interesting features, and it's definitely kind of weird. Here's another set of what you might call matrix multiplications, even though this is a row, we might consider it a row vector, and this is a column. We're going to do A times B and then B times A, and these all have special names. We're going to extensively look into what our text likes to call the inner product when we're way out in chapter 6. Turns out the inner product is the way to investigate the geometry of a vector space. And remember, a vector space could be anything. It could be a set of functions. So inner product could let you measure the angle between vectors. We can measure the angle between square root of t and t squared, in other words, in a different kind of vector space. The way the inner product works is we take a row vector, like this one, multiply a column vector like this one, A times B is going to be 3, 2, 1, times the column vector 2, 3, 0. It looks funny at first, but really it's just like getting one entry in that matrix multiplication we just did. This is of size 1 by 3, column vectors of size 3 by 1. So the result we get is of size 1 by 1. This is the one and only time we wouldn't put a bracket around it. I mean, you could, no one's going to stop you, but a matrix with exactly one entry is just a scalar. So we drop the bracket in this case. We're just multiplying the corresponding entries together, adding them up. So this would be 6 plus 6 plus 0 for a result of 12 altogether. Well, that's our just first look of the inner product function. We'll have a lot to say about that in chapter 6. The next one, B times A, is the outer product. Our book doesn't discuss this a lot, but if you're taking a lot of math, lots of applied mathematics, there are a ton of applications to this. If you're going to take a lot of physics, quantum field theory, quantum computation theory is a part of the outer product. Also, practical things like image processing, signal processing use the outer product, which is that multiplication, B times A. So B times A goes like this, 2, 3, 0. Let me fix that 0 first. Multiplying 3, 2, 1. This multiplication is valid as well because the column vector is of size 1 by 3. The row vector is of size, excuse me, I got those backwards. Let me try again. The column vector has 3 rows, so it's of size 3 by 1, struggling with dimensions today. This is 1 row, so 1 by 3, 3 columns. That tells us the result is going to be a full-on 3 by 3 matrix. So whereas the inner product gives us a scalar, we have now for the outer product a matrix when we combine those vectors in that order of multiplication. The same idea applies to how we did the matrix multiplication first. We start on column 1. We use column 1 right here to build out column 1 of the product. Then we just go across the rows. Take 2 times 3 for a 6. Move down a row, it's 3 times 3 for a 9. Down a row again, 0 times 3 for a 0. And that builds out our column 1 in the product. Kind of a weird view, but if you look at the example right above, where we took B times A, we were doing the same exact thing. We just had more columns right here. This time it's just one column. Then we just move down to the next column. To build out this column right here, we go to the second column here and do the same exact operations. First, it's 2 times 2 for a 4, 3 times 2 for a 6, 0 times 2 for 0, and then repeat. Last column here is built off multiplying this column. Same pattern. So this will give us a 2, a 3, and then a 0. The red dot is meant to be kind of where your finger might have been or where your eyes are looking as you work through. And this is our resulting matrix. Somehow, some way, this outer product is tied into a huge amount of applications. I mean, so is the inner product. This one is just as important. We'll investigate it ourselves. But bigger call outs to the outer product because our textbook doesn't say much about it, but it does have a really important role in mathematics and applied mathematics as well. Well, any questions, folks, with those kind of unusual multiplications? Okay, there'll be a couple of these to practice with as well in the homework. Then more facts about matrix multiplication come up. We have a nice theorem that says, first, things look pretty normal when we take a look at this. We'll look at the warning in a second. If A is an n by n matrix and the matrices B and C have sizes which make these multiplications and sums compatible. In other words, this whole sentence is just saying, assume everything is defined, force the sizes to be right to make it so. IM is the m by m square identity matrix. Then we have nice properties of multiplication as an operation. Matrix multiplication is associative, is what this row is saying. It follows a distributive law. A times B plus C, you can just distribute and take AB plus AC. You can distribute from the left. You can distribute from the right and nothing goes wrong. And we also have a kind of associativity. If R is a scalar, you can either do A times B, then scale by R, or you can scale A by R first and then multiply the result by B, or why not just scale B by R first, whichever is most convenient, and then multiply it by A. This one's important as well. This tells us the identity matrix is the identity operator for matrix multiplication. So identity matrix times any matrix A brings back that matrix A, whether you pre-multiplied it or post-multiplied it. Notice we're being pretty specific on a lot of these properties, that if you can do it one way, you should be able to do it the other way. It turns out we have to be really, really specific because this is the one thing we lose in matrix multiplication. We lose commutativity, and that is really kind of crazy. In the field R, commutativity says x times y is equal to y times x. And it's just a property we take for granted pretty much from the first time we started thinking about multiplication. 4 by 3 is the same as 3 by 4. But we lose commutativity, a pillar of that property from the field R, when we go to matrix multiplication. So at this point, A times B equals B times A is special. When that happens, we say the matrices A and B commute with each other, but that's not something we can take for granted. That's a property that fails in general. So here are the warnings. A times B in general is not actually equal to B times A. And it gets even weirder. If you have an equation, and we solve a lot of equations in the field R back in the day with algebra, but in this equation right here, there's no cancellation law. A times B equals A times C doesn't necessarily mean B equals C, and that's really weird as well. It gets even worse. There's no zero product property. The review of the zero product property says you can find non-zero matrices, A times B, have them equal to 0 after you take the product when neither A was 0 nor B was 0. The loss of that property is extremely huge to us because back again in the field R, if we're solving equations, say this polynomial equation, we took advantage of the zero product property almost as a second nature. We would factor the equation and say with one thing times another thing equals 0, then either the first factor was 0 or the second factor was 0, and that just gave us immediate solutions. We lose that when it comes to matrix multiplication. So there's lots of things that go wrong, but we can fix a lot of them, in particular solving equations when they come up, by dealing with the matrix inverse. The other sad thing is not all matrices have an inverse, so that's another challenge that we have to get through. So The big warning here, the big takeaway is A times B is not equal to B times A. Algebra doesn't work the way you think it should. And we'll investigate that ourselves down below here. So you'll have a version of this as well in the homework. Here's just two ordinary looking matrices. None of them are the zero matrix, although the zero row is kind of suspicious here. We're going to use this as a counterexample to show matrix multiplication is non-commutative. That means if we're going to show this, we have to literally multiply A times B and multiply B times A. Along the way, we'll discuss how the zero product properties failed at the same time. But this is just another set of practice for us as well, looking into how these properties are failing. So for A times B first, they're both square of the same size, so they're definitely defined. The result is going to be a square matrix of the same size as well. Multiplying A times B, let's do this carefully because we're still learning this. To build out this column, just focus on this column right here. Then going row-wise, 1 by -3 gives us -3, plus 3 times 1. So this is 3 minus 3 for a 0. Then do it again, but this is a 0 row, so it's just going to be 0 plus 0. And our first column goes to 0 on this one. Then to build out this column, we focus on this one and do it all over again. This will be multiplying corresponding entries, -3 plus +3. So 0 again. Zeros here will say 0 plus 0, so 0 again. And we got the 0 matrix. So that's this part right here. Neither A nor B was 0. This is impossible in the real number system. But here we have shown the 0 product property failed. And this is a huge loss for algebra because it now means solving equations, we have to work a lot harder. We can't take advantage of A times B resulting in 0, meaning either A or B was 0 any longer. So we lose all that. Now we'll try it again with B times A, see how commutativity is lost at the same time. But any questions at the moment? Okay, well, A times B, B times A now. The matrix B is -3, 1. -3, 1. The matrix A goes 1, 0, 3, 0. So for this column, we'll focus on that column. Numbers we'll pick up will be -3 plus 0. So just -3 here. Down to row 2, this will be 1 times 1 for a 1 plus 1 times 0. So just 1 plus 0 for a 1. Next, we skip over to this column and do the same. This will be -9 plus 0. So -9 in total. Then it'll be 3 plus 0 for 3 in total. And it's a totally different matrix. None of the entries were 0 on here, but just one non-zero entry means B times A is not A times B. So putting those multiplications together, we can say, therefore, A times B is not B times A, and commutativity fails. Sometimes it works, but not for these matrices. We can clearly see we get different entries when we attempt the result. Well, any last questions, folks, on looking into these loss of features and matrix algebra? Okay, as a vector space, it's a great structure, the set of all m by n matrices. Vector addition, scalar multiplication works just the way we think it would. It's when we look into this new structure, when we start looking into matrix multiplication, that's properties beyond a vector space. And it's a very strange algebraic property indeed, losing these features. Last couple things we'll take a look into are operations we might need later on, like the transpose. But really, example 6 and example 7 is just a little bit more practice doing matrix multiplication. It's really, really fundamental. We'll be using it quite a lot in this chapter 2 and chapters beyond. So here's our extra practice and also the new thing, a matrix transpose. This will be useful again down the line when we're way out in chapter 5. It feels like a lot of the stuff we're looking into is all pushed into chapters 4 and 5. The way the transpose goes is if you start with an m by n matrix A, the transpose of that matrix, denoted by A with a superscript of T for transpose, is now of size n by m. And all we do is we take the columns and swap them with the rows. So column 1 in this matrix becomes row 1 in the transpose. And that's why it becomes from m by n to n by m. So just a full swap. Same kind of operation if you transpose a grouping of numbers or an array in, say, Excel, you're doing the same kind of thing. And matrix transpose has its own set of properties. This one seems about right. Transposing once is swapping the rows with the columns. Transpose again, and you swap the rows with the columns again, but you just undid the operation. So it returns back the original matrix A. This one's kind of a nice one. It gives you options. If you're adding the matrices, you can transpose after adding them, or you can transpose before you add them and you get the same result. This tells us that scalar multiplication is totally unaffected by transposing. So either scale the matrix first or later and you get the same result there. And this one's a kind of a surprise. A times B transpose has to be B transpose times A transpose. And there's maybe a good way to think about why that property ought to be true. If A is of size, let's say 2 by 3, B is of size 3 by 2, then you go to, say, take A times B. This result is going to be of size 2 by 2. Now, if you take a look into A transpose, it's of size 3 by 2. B transpose is of size 2 by 3. And if you take, say, something like, hang on, let me take a look at this. Let me make it maybe slightly different. How about a 4 there, just to mess it up a little bit? The resulting product here is now 2 by 4, so I had to fix that there as well. And this would be 4 by 3. So now this is about what I was expecting to show. A transpose times B transpose, that would be a size 3 by 2 multiplying a size 4 by 3. So this is undefined. But it turns out if you do it in this specific order, B transpose times A transpose, then, well, B transpose, it'll be the 4 by 3. A transpose is going to be size 3 by 2. And that would work. This would result in a 4 by 2 matrix. As it should, because if we transpose A times B up here, it's 2 by 4. The transpose of it should be 4 by 2. So what this is telling you is you have options. If you want, you can transpose after you multiply A times B. If you want to transpose later, or excuse me, if you want to transpose first, you have to reverse the order of the matrix multiplication, or potentially the whole thing is undefined, as we fixed it here to force that outcome to occur. So that's the transposition operator. And down the line here is just a couple extra practice problems, really more about matrix multiplication than anything. First, any questions about matrix transposing? Okay, let's try this one out. This one doesn't even have a transpose on it. We're just taking A times B. This goes 2, 6, negative 2, 1, 3, 4, multiplying 2, negative 1, 1, 6. I should have probably looked at this before I wrote it down. We want to check if it's defined. Matrix A is of size 3 by 2. Matrix B is of size 2 by 2. So it is defined, inner dimensions match. The resulting product will be of size 3 by 2. Let me fix that. That doesn't even look 3 by 2. There we go. Looking in the outer dimensions, 3 by 2 gives us the size of the product. Now, using column 1, all we're doing is recopying the skill in section 1.4 of taking a matrix times this vector. Pretend 1,6 isn't even there, and you're doing it just right. Just place your result in that column. So this will be 4 minus 1 for a 3. This will be 12 minus 3 for a 9. Then -4 minus 4 for a -8. And that fills out to our column 1. To get column 2, we now fixate on 1,6. Pretend nothing else exists in the matrix B. 2, -1 is just invisible to us. The entries we'll get this time are going to be 2 plus 6. So an 8, 6 plus 18. So that's going to be 24. Then -2 plus 24. So that's going to take us to a 22. And that should be the result of A times B, unless I messed up my arithmetic somewhere. Does that look right to folks so far? Okay, finally, here's the new thing. We want to take A times B transpose. So with the result that we just computed, we already know what A times B is. That means A times B transpose would result in, following the definition above, you're going to take the columns and form it from the corresponding rows. So if we do that, that would mean the new size of this is 2 by 3. That's the part that's highlighted in yellow here. Transpose is going to literally swap the rows and the columns. And you can really do this in any order. You could take the column and make it the row. If you're doing this verbatim, then you might be taking the row and making it a column. So 3,8 is column 1. 924 is column 2 of the transpose. And -822 is column 3. But that's just the same as taking this whole column 1 and making it a row 1, and taking this whole column 2 and making it a row 2. Either way, we have AB transpose. Last thing we have to calculate is AB transpose times A transpose. And that could be a lot of extra work, but recall that B transpose times A transpose is just AB transpose, which is this result. We don't have to do it all over again. That's just the content of that part right here on the theorem. Out of nowhere, it feels like a really good computational theorem to have right here because it was a reminder we've already done this computation. Well, that's pretty much all we have to say about the transposes on this one. Any last questions or comments before we try out the last example? Okay, well, one more kind of 2 review topics we're going to take a look into. We have 2 square matrices, 3 by 3. All we're going to do is compute these 2 things just for the sake of extra practice. I mean, 2.1 is matrix operations, so we're doing lots of a matrix arithmetic. First one is A transpose times B. So what I would do is definitely copy this in carefully. A transpose, I'll go along the rows and make them a column. So 314 as a row is a column 314. -201 goes in this way. And row 3 is column 3, 1, 2, 2. Then it's multiplied by the matrix B. 1, -3, 2, 0, 1, -4, 2, 1, 1. They're square matrices of size 3 by 3, so automatically it's defined, and automatically the result is also 3 by 3. And here's essentially all we do. Avoid carefully, this is our last big matrix multiplication. When we do Column one right here, all we're doing to get the first entry in that position is taking 3 times 1 for a 3, 2 times negative 2 times negative 3 for a 6, so we're up to 9, plus 2 to give us an 11. So just loads of arithmetic. Linear algebra is kind of a weird class. It felt like last class was more about theory than anything, and this one's more about arithmetic than anything. So now this will be 1 plus 0 plus 4 for a 5. And last product, really these are just inner products or dot products, putting down the results. This will be a 4 minus 3 for a 1, plus a 4 for a 5. Then we move over to column 2 of the matrix B to build out column 2 of the product. And same thing, I'll stop highlighting this one. We're just going to go down the rows in the corresponding product. So this will be 0, negative 2 times 1 for a 2, 1 times negative 4 for a negative 6. Then on this row, this will be 0 plus 0 minus 8. And multiplying, adding as we go, this will be 0 plus 1 minus 8, so a negative 7. Then move over to the next position. And same exact property. All we're doing is focusing on building out the third column. This will be 6 minus 2, so we're down to 4, plus 1, so we're up to 5. Then it's going to be 2 plus 0 plus 2, so 4 on that one. Then it's 8 plus 1 for a 9, plus 2 for an 11. So providing you didn't mess up any of those numbers, that's the product A transpose times B altogether. Kind of an interesting matrix. We'll have more to say about matrix multiplication when we're in the later section, 2.3. But any questions so far, folks, getting that one down? Okay, let's try this out all over again. Well, not exactly all over again. This is a different kind of problem altogether. This one's just a linear combination. So now we're working with the vector space properties of matrix operations. Notice that I is a little bit tricky. Well, we do have to use the context on this. These are 3 by 3 matrices, so that I bumped up with the context, we have to think of as being 3 by 3. I usually try not to write that way in an exam setting because, again, it's good to be really specific on exams. But you'll see a lot of this kind of stuff in the homework. We sometimes have to think the context to do the property. So first thing I'm going to do is just place down 2 times A transpose. And notice we already have A transpose down. A transpose is this matrix. So all we need to do really to get started is scale it by 2. So that's the property for transposes right up here. The order we scale is irrelevant. We can either do A transpose first and then scale, or we can scale the matrix and then transpose it later. Either way, you get the same thing. So these are really just properties we take for granted, where this was probably the bigger special one. Scaling this by 2 gives us 6, 2, 8. Then negative 4, 0, 2, and then 2, 4, 4. Now this one, I feel like this would be doing a lot for me mentally all at once. What I would do first is, before just scaling by negative 3 and taking the transpose, let me just put somewhere on paper what B transpose is. Gives us something to look at. So going along the rows, column 1 is 1, 0, 2. Column 2 is negative 3, 1, 1. And column 3 is going to be 2, negative 4, 1. So now I've got B transpose there. I'm going to scale it by negative 3. And this will be the result of that entire second term. Scaled by negative 3, we've got negative 3, 0, negative 6. Then 9, negative 3, negative 3. Then negative 6, 12, negative 3. And almost there, we are also adding the identity matrix, which is a diagonal matrix placing ones. Let me try again. Placing ones on the main diagonal. So not that quite. That's better. So here is I, where we sized it to match the context of the linear combination we were forming. At this point, really the problem is over. We just have to be careful with our eyes. So this is the 1, 1 position. We'll go to the corresponding 1, 1 positions for every matrix across all three terms and just add. So 6 plus -3 plus 1 is going to give us a 4 altogether. That took me a second. I guess I'm getting tired. Then when we're on the off diagonal, this matrix has no bearing. It's only going to affect our main diagonals. So I'm just thinking these two matrices on the next values. I'll go row-wise, it looks like. So -4 plus 9 for a 5. 2 minus 6 for a -4. 2 plus 0 for a 2. This one involves a main diagonal. So it's 0 minus 3 plus 1 for a -2. Then back to just the blue and green matrix. So 4 plus 12 for a 16. 8 minus 6 for a 2. 2 minus 3 for a -1. And we're on the main diagonal again, so all three matrices. 4 minus 3 for a 1, plus 1, giving us a 2. So that's the resulting linear combination. It's a ton of arithmetic. Hopefully I didn't mess up any of the numbers. Let me know if you ever see something weird on the notes. I do go back and correct them whenever you spot them. But any questions at all, folks, with the matrix operations so far? Okay, fun fact, I think this is the first class all semester. I could be wrong about that, but we didn't use a single row operation this entire time. So that's kind of unusual as well for linear algebra this semester. The next set of notes, I don't think I want to get too far into with our limited amount of time, but maybe just discuss a couple topics on the warm-up page. We'll do example 1 once we really get going. But in this section, we will use row operations. Matrix multiplication is trying to do the thing that we didn't do in section 2.1. We can't divide by a matrix. We go for the next closest topic, multiplying by its multiplicative inverse when it exists. And the big analogy is the field of real numbers, which we have learned since we were in elementary school, high school, and so on. We're very familiar with how things go here. And we really didn't have to divide things. We can multiply by the multiplicative inverse in the field of real numbers R as well. So in the field of real numbers, a real number A, so A is the object, and that's just the indefinite article. Italics means the mathematical object. A real number A has multiplicative inverse whenever A is non-zero. So just a fast example for the sake of the analogy. Take the number 5. 5 has multiplicative inverse, 5 inverse, since 5 times 5 inverse. Here, well, 5 inverse is, that's just an exponent. That's just 1 over 5. So you could work in that sense. This is 5 times 1 over 5. If you like exponents, you could just say this is a power 1, then a power -1. That would give you 5 power 0. Anything non-zero to the 0th power is 1. And we get this new thing. 1 is referred to as the multiplicative identity in the field of real numbers because 1 times any real number whatsoever will return that real number. So this is how it worked back in the day. Now we're extending all of these topics to matrix multiplication. So this is how the analogy connects with what we're about to do. Notice the restriction here. Our definition for a matrix inverse already is restrictive. A must be square. We do not have a topic in this book for inverting a 2x3 matrix, for example. The more linear algebra you do, the more you see that they try to get as close to that as possible. There is a concept called the pseudo inverse for a 3x5 matrix, trying to gather as many properties as possible. But our text is only going to deal with square matrices that gives us the true inverse. The matrix A is invertible if there's another square matrix of the same size, call it C, such that when we pre-multiply C times A, we get the identity. That's the multiplicative inverse for matrix multiplication, because the identity times any matrix gives that matrix back. But we have to do a little bit more. Here, we have commutativity of the field of real numbers. We lost commutativity in general, so this definition has two parts. We also have to be able to post-multiply A by C to get the identity matrix I as well. This is what the core definition looks like. But if you look into this further on, if you previewed section 2.3, you might already know a matrix will commute when it's inverse, and that's just one exception. When it comes to the core definition, though, you have to say it this way, because that's a theorem that has to be proved later on, that C times A would be equal to A times C whenever you have the inverse. Looks like that's the case, right? If you've got the identity matrix on both sides. And this is what matrix multiplication looks like. There's the identity matrix as well. And if we write in terms of A inverse, A times A inverse will equal to A, and equal the identity matrix I. Multiplying in a different order, we'll get I as well. So it's really clunky to have both of these definitions here and here. It's weird that it's not defined just once, and that's because we didn't have commutativity just yet. But later on, theorems will tell us if this works, then C is in fact an inverse. You don't have to check the second equation. It will happen by default. But for us, if we're just using the definition, we need to show both multiplications until we actually start using and citing that related theorem. Well, again, I don't want to go too far on the notes. We'll be looking into verifying if this, as ugly as it looks, really is an inverse to A by doing this multiplication and this multiplication as well. That will be what we get into at the start of our next class on Tuesday. So any questions at all, folks, about matrix multiplication so far? Okay, there's loads of things to say about it. And we're getting really close to that big theorem, the so-called invertible matrix theorem, which extends all the topics in theorem 4 of chapter 1, but only for square matrices. So that's going to be our big topic we're going to look into on our week 7. But have a great weekend, folks. I'll try to get the exam 2 information and review prompts posted early on Friday, probably sometime around the afternoon, 12 or 1 o'clock. If you have any questions while you're studying, working on homework, don't hesitate to reach out. I'll be happy to help. But take care. I'll see you all next week.